I've made a lot of videos, but a recent one,
All right, this is not the right one. Ooh.
I've made a lot of videos, but a recent one somehow engaged many viewers. This video was about why light slows down when it enters water, glass, or any transparent medium. For some reason, this video took off, and the comments were very interesting, covering the entire gamut of claiming that the video was insightful to claiming that it was utter rubbish. But one particular question appeared over and over again, and that comment was, but why does light bend when it goes from air to glass? And it's true that I didn't answer that question because, well, it wasn't what the video was about. But a lot of people ask, so in this video, I thought I'd tell you why. Now, as it happens, there are lots of wrong explanations out there, lots. So the first thing I'm going to do is tell you the wrong ones and why they're wrong. Don't be surprised if I debunk one you learned. So let's start with what we see when a beam of light hits glass. Light traveling through air will change its direction when it hits the surface. The amount that its direction will change depends on the angle at which it hits the surface. Change the incident angle, and the transmitted angle will change correspondingly. Those angles are related through a physics formula called Snell's law, named after Dutch astronomer Willibord Snellius, who lived in the 1600s. I have his formula written over here. If you'd like to learn how to use the formula, there are many online tutorials, but I'm not going to cover that here because I want to get into the question of what is the physical process that causes the path of light to change as it enters the glass. So let's get into it. There are three commonly suggested explanations that are wrong, or at least incomplete. They are Fermat's principle, the analogy of soldiers marching, and Huygens principle. Fermat's principle says that light will travel from one point to the other, taking the minimum amount of time. It's often explained in terms of a lifeguard and a drowning swimmer. In order to maximize the chances that the swimmer will be saved, the lifeguard needs to get to them as soon as possible. So what path does the lifeguard take? He could run directly to the water and start swimming. This means he would swim a long distance, but because he can run so much faster than he can swim, that would be a bad choice. So you'd think that he might just run over to the point where the swimming portion is shortest, but that turns out not to be the shortest time either. Then there's the straight line path, and because the shortest distance between 2 points is a straight line, you might think that this is the fastest path. But because swimming is slower, it still isn't the shortest time. It turns out that the shortest total time, that is to say when you add both running and swimming time, is exactly what you get from Snell's law for light. You run a little longer than you would for the straightest path, but that means that you swim a little less and the total time is shortest. And that's exactly what light does. It follows the path of shortest time. But while that's true, it doesn't explain anything. It just says what it does, not why it does it. So that's not an explanation, and we need to come up with a proper reason. Let's look at the second option on the list. A very common explanation used to teach why light bends involves soldiers marching over firm ground, but then who encounter mud, although not all soldiers hit mud at the same time. The idea is simple. The first soldier who encounters the mud cannot move as quickly as the rest of the soldiers, so he slows down. Each soldier hits the mud in turn, resulting in a direction change. Eventually, the lines of soldiers are moving in a different direction at a different speed. This is how it's often taught. The problem is that this doesn't work. In fact, the soldiers will slow down, but their direction doesn't change. They will continue to walk in the same direction, but with marching lines that are slanted compared to how they started. This explanation gets the angle of the lines of soldiers right, but not the direction of travel. In fact, the only way that this explanation can be right is if the lines of soldiers are rigid. Then, the first soldier hitting the mud puts a torque on the entire line, and that would work. The problem is that this torque means that the soldiers on the top of the screen move faster, which is to say that if they were light, this part of the beam of light would have to move faster than light. So this explanation doesn't work either. Okay, so far we have a non-explanation and a wrong explanation. What about Huygens principle? Huygens principle, named after Dutch physicist Christian Huygens, depends crucially on the wave nature of light. We know that when a wave encounters a small gap, the wave passes through the gap and spreads out. This principle is called diffraction, and it's universal to all waves. If waves hit more than one gap, each gap will allow waves to pass through and make ringlets. The waves from each gap can interfere with one another, with the waves either adding to or subtracting from one another. In this animation, the lines show the position of the peak of the waves. Showing how the waves add together is perhaps easier looking at them from the side. When the peak of two waves encounter one another, the result is a single and bigger wave. And when a peak of one wave hits the trough of another wave, they can cancel each other out entirely. What Huygens claimed is that there is no need for gaps. Each and every spot on a wave was acting like it went through a gap and was spreading out. Now we can take that idea and have waves moving in one medium transition to another medium where the speed is different. So we can take light traveling through air and shoot it through glass. And because we're interested in explaining the bending behavior, we'll have light hit it at an angle. Here's how the Huygens explanation goes. What happens is that the wave peaks hit the glass at different times. The waves then spread out and begin to interfere with one another. Notice that the wavelength is shorter in glass. That's because the wave is moving more slowly. Where the lines accumulate, that's where the waves add to one another. And they don't just line up in one spot. They line up again and again. Remember that the lines denote the top of the peaks of the waves. We can see that there are many places where the peaks line up. We can overlay a couple of lines that show the direction that the wave is traveling and then remove the circular waves, and we see that this explanation seems to be doing a good job of predicting what happens when light goes from air to glass. Looks good, right? But not so fast. What happens when we look at all of the waves coming through the glass? Things get a lot more complicated. We do see that the waves add together to predict the direction that light moves in glass. On the other hand, that's not the only alignment. For instance, we see other geometries where the waves line up. There are the wave fronts that are going this way, and then there are the wave fronts going this way. So that's a problem. It seems that this approach doesn't give a unique prediction. Okay, we've ruled out Fermat's principle, the soldier analogy, and Huygens principle. These are all often seen as explanations of the cause of refraction given by people who really do know some physics. So what's the real answer? It turns out that the only way to really answer the question of why light bends when it goes from air to glass is to get serious about the nature of light and to embrace the fact that it is made of oscillating electromagnetic fields, and that means you need Maxwell's equations. Because this isn't a full-blown physics class, I'm going to focus only on the electric fields, and I'm not going to do the derivation because that's the fun part. I'll leave that to you. But the big ideas are actually pretty straightforward. You start with Maxwell's equations, which are always beautiful to see. They're a little scary looking, but the question we're trying to answer is an easy one, which makes the whole thing a lot simpler than you'd imagine. In fact, we're going to need only the bottom two equations. So let's see what's going on. We start with light going from air to glass, hitting the surface at an angle. In our figure, we can replace the waves with the direction of motion. Now it turns out that the electric field of light is perpendicular to the direction that light is traveling, and we can add that field direction to the diagram. And it's very important to remember that this field has a component both parallel to the surface of the glass and one that is perpendicular to the glass. And here is where Maxwell's equations come into play. Two copies of the equations are written here, one that covers when light is traveling in air and one where it is traveling in glass. So here's the key point. The surface belongs to both the air region and the glass region. This means that at the surface, the equations on the top and the equations on the bottom have to apply. And with that little bit of calculus, you can find two important restrictions. The first is that the electric field parallel to the surface of the glass has to be the same in the air and the glass. And similarly, perpendicular to the surface, what has to be the same is the electric field times this epsilon, which is different for each material and depends on its molecular makeup. We can then manipulate these equations to see what the electric field in glass should look like. Because epsilon is bigger in glass than in air, that means that the perpendicular electric field in glass has to be smaller than it is in air. Now we remember that the direction the light travels is perpendicular to the electric field, so we can put in an arrow to show the direction light must travel in the glass. And finally, we can see what light does when it enters glass or water or any transparent medium. It bends. And the reason that it bends is because the epsilon in glass is bigger than in air. Okay, what I just showed you is an equation thing. You're probably asking yourself what that epsilon actually physically means. It's there because of how the electric fields from the light interacts with the matter in the glass. You start out with glass with no electric field in it. The glass has charges in it, but they're arranged in a random way. But when you send light in, you impose an electric field on it. That field makes the charges move around, which sets up a counterbalancing electric field from the charges. The result is that the electric field in the glass is lower than it is in air because of how the electric field from the glass is in the opposite direction. And this is the reason that the perpendicular electric field is lower in glass. And that, my friends, is why light bends when it goes from air to glass. It's not because of many of the ordinary explanations. It's because of how light interacts with glass and changes the glass's properties. And it's because the electric field inside the glass is affected by the arrangements of atoms and molecules in the glass when light hits it. It's the same reason why light slows down in matter. Inside matter, the electric field due to the light and the electric field due to the matter both have to be taken into account. Outside, they don't. And now, you know some serious physics. Okay, so that was a very long video. It kind of had to be to cover the many incomplete or wrong explanations and then explain the correct cause. And I imagine that some of you will ask about the quantum explanation, which is similar to the one I told you here using Maxwell equations, except using energy and momentum of the photons instead. There's always more to learn in physics, always more. And you do that because, of course, physics is everything.
All right, so that was a really good explanation. So let's go back in case there's some test questions. So I want you to be able to figure things out. All right, so the correct explanation that he finally came up with is the one that we're interested in. So you got this is the light ray, and then so what's going to happen to the light ray? It's got the electric field component, magnetic field component. We're only interested in the electric field component of the light ray. It's going to be perpendicular to the direction of the light ray that we came up with. All right, so it's going to have the electric field component is going to have two components. Okay, this is a vector. It's going to have a component which is parallel to the surface. It's also going to have a component which is perpendicular to the surface. It's talking about the epsilons, something that we discussed before. It tells you how much the sort of effect that the epsilon has on the electric field component. In essence, it puts the brakes on. So what that mathematically, what this means is it's going to slow it down more. The electric field component is going to get slowed down more in glass. That's what it means from a mathematical perspective. Oh, what does it mean in terms of physics? That's what we are discussing right now. So the next thing that he does is going to bring up the Gauss's, not the Gauss's, the Maxwell's laws. This is within the more advanced representation of it is a cross product representation that we're using here, which means that the change in the strength of the magnetic field within a certain region is going to cause a circulating electric fields. That's what it means. So this is the Gauss's law that we were referring to. So the strength of the electric field within a certain region enclosed within a Gaussian region is going to depend on the net charge on the inside. All right, so you're looking at the charge density. So what he's saying in essence is air and glass is going to share a common border, and within the border, certain things will happen. So these equations will be equal to each other from a mathematical perspective. But I'm more interested in the conceptual explanation that he provided. In essence, what he's saying is after the refraction, all right, let's just go forward. This is trying to explain it. All right, so once again, if you're looking at this electric field component of the wave, once it gets across the boundary, parallel component is going to remain the same. All right, so which means that the magnitude of the parallel component is going to remain the same, but the vertical component is going to become affected by the medium itself. So the vertical component is going to get much shorter instead of being this. All right, so the perpendicular to vertical component is going to become shorter within this region. So the question is why? All right, so he explains it in terms of epsilon not being larger, but that's more of a mathematical look at it. The real reason that he came up with is the one that I'm interested in. So what happens within neutral surfaces under the influence of an external electric field? This is something that we discussed the first week on. So what's going to happen is the surface is going to become polarized, right? All right, so whoever the animator is just messed up the direction of the charges. The electric field pointing in this direction is going to push the positive charges into the surface and pull the negative charges up. All right, and so the induced electric field is going to be pointing in the opposite direction. That's what they're trying to say, but this person got it wrong. As a result, the resultant electric field is going to get smaller, and because the resultant electric field is getting smaller, the vertical component, all right, the perpendicular component of the vertical component is going to become smaller. All right, in case there's a test question, this is the answer that I'm looking for. All right, now we end up coming up with a new vector. So here's the perpendicular component of the electric field vector. Parallel component doesn't change. So when you come up with the resultant vector, it's going to point in a different direction. And because this resultant vector is pointing in a different direction from the original one, if you have to draw a line which is perpendicular to the new electric field line, notice that it's actually going to be, it's going to change direction, and it's going to bend towards the normal. All right, so the next thing that we need to kind of focus on is the fact that as the light changes medium, not only it's going to slow down and change direction, but also the fact that its wavelength is going to get shorter. All right, so the question is why?
When a light beam, incident at an angle, first encounters a piece of glass, one side is slowed down before the other.
All right, so notice that the wavelength is going to become shorter.
Forcing the wave.
So the question is why? The wavelength is going to become shorter because the wave speed is a combination of wavelength as well as frequency. At the boundary, the frequency is going to remain constant. So the question is why? Why is it that the frequency remains constant? We discussed this before, but let's discuss it again. Imagine that this is a time period, 1 second time period. So we have you got 1, 2, 3 wavelengths approaching, or wavefronts approaching, and notice that 1, 2, 3 of them will be crossing at the same time. So number of wavelengths approaching within the same time period is going to be the same as the number of wavelengths crossing the boundary, or the number of wavefronts approaching and crossing the boundary within the same time period is going to be the same. So remember, the frequency is the number of seconds per second, number of periods per second, number of wavelengths per second. In this case, it's going to be the number of wavefronts per second. All right, so frequency is going to be the same between the incoming as well as the the waves crossing the boundary, incoming as well as the ones crossing the boundary. And because the wave is going to slow down, the only thing that happens is the wavelength is going to become shorter.